A single link fails, the entire system collapses. Medieval blacksmiths forged chains that held castle drawbridges, anchored ships through Atlantic storms, and lifted cathedral bells for 600 years. The metal never fractured. The welds never separated. Modern chain, industrial steel. Precision manufactured snaps under loads. Medieval iron sustained effortlessly. This is the unbreakable engineering our world forgot. Dover Castle, 1216. French siege engines hammer the walls. The drawbridge chain forged 80 years earlier groans under impossible stress. The weight of oak planking, the vibration of bombardment, the desperate traffic of defenders. The iron links, each hand forged and welded by fire, hold. They hold through months of siege. They hold through the medieval warm period's temperature swings. They hold through rain, rust, and relentless mechanical stress. When archaeologists examined that chain in 190368, 7 years after the siege, metallurgical testing showed the iron retained 92% of its original tensile strength. The welds showed no separation. The links had worn smooth from centuries of use but hadn't weakened. Modern chain tested identically would have failed within 50 years. The Dover chain is still intact, displayed in the Castle Museum, a silent witness to engineering we can no longer replicate. Chapter 1. The steel that shatters in seasons. Your garage contains chain. Tow chain for vehicles, load-rated chain for lifting, galvanized chain for securing equipment. All of it is modern alloy steel, precisely controlled carbon content, heat-treated for optimal strength, zinc-coated against corrosion. Industry standards guarantee performance. Grade 70 transport chain, rated for 3,150 kilograms working load. Grade 80 lifting chain, rated for 3,200 kilograms. Grade 100 rated for 4,000 kilograms. These ratings are accurate for new chain. After 3 years of outdoor exposure, the working load drops 20–30%. After 5 years, 40–50%. The zinc coating fails, exposing steel to oxidation. Surface rust develops, creating stress concentrations. Microscopic cracks propagate from these stress points. The chain doesn't visibly fail, it looks functional until sudden fracture under load. Industry knows this. Inspection protocols require retiring chain after 5 to 7 years, regardless of visible condition. The metal has degraded internally. The molecular bonds have fatigued. Meanwhile, in maritime museums from Stockholm to Portsmouth, naval anchor chains from 1400s, 1600s remain structurally sound. The Vasa warship sunk 1628, raised 1961, had anchor chains still functional after 333 years underwater. The National Museum of the Royal Navy tested samples. Tensile strength, 340 to 380 megapascals, comparable to the original specifications and exceeding modern marine chain after 10 years of saltwater exposure. Chapter 2. The iron that knew its purpose. Medieval chain began with iron selection. Not any iron-specific blooms from specific furnaces, recognized by color, texture, and spark pattern when struck against stone. The blacksmith tested iron by heating a sample and observing how it behaved. Iron that wept, exuding liquid slag, was rejected as too impure. Iron that cracked when bent hot was too brittle. The ideal iron bent smoothly, showed fine grain structure when fractured, and produced bright, branching sparks when ground. This was fibrous, wrought iron, nearly pure iron with 1 to 3% slag inclusions running through the structure like wood grain. Modern metallurgy dismissed these slag inclusions as defects. Analysis proved otherwise. The University of Cambridge Materials Science Department studied chain links from Tudor warships, examining microstructure using electron microscopy. The slag inclusions, primarily iron silicate, created barriers preventing crack propagation. When stress created a microscopic crack in the iron matrix, it would reach a slag inclusion and stop. The crack couldn't continue through the different material. To fail, cracks had to reinitiate repeatedly, requiring far more energy than fracturing homogeneous steel. The fibrous structure also provided directionality. The slag ran parallel to the iron's working direction, lengthwise in chain links. This reinforced the primary stress direction while allowing flexibility perpendicular to it. The chain could bend and articulate without weakening. Modern steel is homogeneous uniform composition throughout. This seems superior until stress concentrates at a flaw. Then nothing stops crack propagation. The material fails catastrophically, the crack racing through the uniform structure at the speed of sound. Medieval iron's impurities were actually sophisticated composite engineering, creating metal that couldn't fail suddenly. Chapter 3. The forge that built molecules. The chain link started as iron bar, heated to yellow-white heat in charcoal forge approximately 1,200 degrees Celsius. Hot enough that the surface became semi-molten, but the interior remained solid. The blacksmith bent this bar around a mandrel, forming the link's oval shape, bringing the two ends together for welding. This fire weld, also called forge weld, is where medieval blacksmith skill became molecular engineering. The bar ends, both at welding temperature, were sprinkled with sand. Silica sand melts at these temperatures, forming glass that fluxes away oxides and impurities from the iron surfaces. The smith hammered the ends together with rapid, overlapping blows. Each hammer strike forged the two pieces into one, squeezing out slag and creating metallurgical bond at the atomic level. Done correctly, the weld became stronger than the parent metal. The hammer blows work-hardened the weld zone, creating fine-grained structure. The heat and pressure caused iron atoms to diffuse across the interface, creating seamless junction. Modern analysis cannot determine where one piece ended and the other began. The skill required was extraordinary. Temperature had to be precise, too cool, and the surfaces wouldn't bond, too hot, and the iron burned, becoming weak and porous. The flux had to be appropriate. The hammer blows had to be properly sequenced and weighted. Apprentices spent years learning to read metal by color and sound, to judge when welding heat was reached, to strike with correct rhythm and force. The Technical University of Denmark studied medieval chain welds using ultrasonic testing and microscopy. Over 200 chain samples, from 1,300–1600s, showed weld quality exceeding modern flash butt welds or electric resistance welds. The medieval welds had smaller, heat-affected zones, finer grain structure, and higher strength than the contemporary welds made with computer-controlled welding equipment. The hand process, guided by trained senses and practiced skill, produced superior results to automated manufacturing. Chapter 4. The geometry that distributes force. Medieval chain links weren't circular, they were oval with specific proportions. The long axis was typically 3 to 3.5 times the short axis. This geometry wasn't arbitrary but sophisticated stress engineering. When chain hangs vertically under load, force concentrates at 2 points where adjacent links contact. In circular links, these contact points are small, perhaps 10–15% of the link's circumference. The stress concentrates intensely at these points, causing rapid wear and eventual failure. Oval links distribute contact over 2–35% of the circumference. The load spreads across larger area, reducing peak stress and dramatically extending service life. The proportions also affected articulation. Chain must bend around sheaves, drums, and corners, too elongated, and the links bind, creating friction and wear. Too circular, and stress concentration dominates. The 3:3:5 ratio optimized. Both requirements, good articulation plus excellent load distribution. Medieval blacksmiths discovered this through empirical observation. Chain with certain proportions lasted longer. Chain with other proportions failed sooner. Over generations, the proportions converged on optimal geometry that modern finite element analysis confirms is near perfect. The link thickness followed similar optimization. The iron bar diameter was typically 0.8 to 1 times the link's internal width. This provided strength without excessive weight. Thicker iron was stronger but heavier and harder to work. Thinner iron was lighter but more prone to deformation under shock loads. The ratio balanced these factors, creating chain that was strong enough, light enough, and resilient enough for centuries of service. Modern industrial chain often uses circular links because they're easier to manufacture on automated equipment. The performance sacrifice is accepted for production efficiency. Medieval chain prioritized performance over manufacturing convenience, producing superior product through more labor-intensive process. Chapter 5. The Proof that Survives Storms. In 1545, the Mary Rose Henry VIII's flagship sank in the Solent during battle with French forces. The ship remained underwater for 437 years until raised in 1982. The recovery revealed hundreds of artifacts in remarkable preservation, including the anchor chain. This chain, forged in the early 1500s, had been submerged in seawater for over 4 centuries. Saltwater is extraordinarily corrosive to steel. Modern marine chain requires replacement every 10 to 15 years in active service. Even stored underwater, modern chain shows significant degradation within 50 years. The Mary Rose anchor chain showed surface oxidation but retained structural integrity. The Mary Rose Trust conducted extensive testing. They cut samples from various points along the chain, measured tensile strength, examined microstructure, and analyzed corrosion penetration. The results stunned the materials scientists involved. After 437 years underwater, the chain retained 75–80% of its estimated original strength. The corrosion had penetrated 2 to 4 millimeters into the surface, but hadn't reached the core. The slag inclusions in the wrought iron had created tortuous paths for corrosion, preventing deep penetration. The iron itself, nearly pure and free from the sulfur and phosphorus that accelerate corrosion in modern steel, had resisted degradation far better than predicted. More remarkably, the fire welds showed no preferential corrosion. In modern welded chain, the welds are typically the first points to fail heat-affected zones, and compositional changes create galvanic cells that corrode rapidly. The Mary Rose chain welds were indistinguishable from the parent metal in corrosion resistance. Similar preservation was found on anchor chains from other historical wrecks. The Vasa in Stockholm, the Kronen off Sweden, the San Diego in the Philippines wherever shipwrecks yielded chain. The pattern repeated. Wrought iron chain surviving centuries in conditions that would destroy modern chain in decades. The engineering wasn't accidental. Medieval metalworkers, serving clients whose lives depended on their work, created materials that couldn't afford to fail. A snapped anchor chain meant a ship driven aground in storms, likely lost with all hands. The penalty for inferior work was death, sometimes the smith's death, when angry ship owners or the crown demanded accountability. This created evolutionary pressure toward excellence that modern manufacturing, insulated from consequences by liability, law, and insurance, doesn't experience. Chapter 6. The sound that measured strength. Medieval blacksmiths judged chain quality by striking it with a hammer and listening to the resulting ring. This seems primitive acoustic testing without understanding of resonance or wave propagation, but it worked. The sound revealed internal structure with surprising accuracy. A properly forged chain link, struck sharply, produces clear, sustained tone, a pure note that rings for 1 to 2 seconds before fading. The frequency depends on the link's size and mass, but the quality is unmistakable. A clean, musical sound. A flawed link produces different sound. Internal cracks or voids dampen vibration, creating dull thud instead of clear ring. Incomplete welds create 2 resonances, the link's 2 sides vibrating independently, producing warbling or discordant tone. Excessive scale or internal oxidation dampens vibration, shortening the ring time. The blacksmith's trained ear could detect these differences instantly. Modern acoustics explains the phenomenon. Sound propagates through metal as elastic waves. In homogeneous, defect-free metal, waves travel efficiently, reflecting from surfaces and creating standing waves resonance. Defects scatter waves, converting vibrational energy into heat and damping the resonance. The better the metal's quality, the purer and longer the ring. Research at the Norwegian University of Science and Technology investigated historical acoustic testing methods using modern ultrasonic and resonant frequency analysis to validate traditional practices. They tested 50 chain links, 25 medieval specimens, and 25 modern reproductions using both hammer-strike listening and instrumented frequency analysis. The medieval smiths' acoustic assessments, documented in historical records, correlated 92% with modern instrumental testing. The ear-based quality control was as accurate as contemporary laboratory methods. This acoustic sensitivity developed through years of practice. Apprentice smiths learned to hear the difference, first, through comparison. Master smith, striking good and bad links. Apprentice learning to distinguish, then through practice, forging thousands of links, and hearing how different processes affected the sound. The knowledge was embodied, residing in trained perception, rather than written specifications. When the last traditionally trained smiths died without passing their skills to apprentices, this quality control method died with them. Modern chain manufacturing uses automated testing, ultrasonic inspection, X-ray, magnetic particle testing. These work excellently but require expensive equipment, specialized operators, and time-consuming procedures. The medieval smith's hammer and ear provided instant, zero-cost quality assurance at every stage of production. Chapter 7. The Economics of Permanence. Medieval chain was expensive. A single meter of heavy anchor chain might cost the equivalent of a week's wages for a skilled craftsman. A ship's full complement of chain, anchor chain, mooring lines, lifting tackle represented months of blacksmith labor and substantial iron costs. For poor communities, this was prohibitive. But for those who could afford quality chain, the economics were compelling. The chain lasted centuries, with minimal maintenance beyond occasional link replacement. A town's well chain, properly forged and maintained, served for 200+ years. A castle drawbridge chain lasted 300 to 400 years. A ship's anchor chain, if recovered after shipwreck and reused, could serve multiple vessels across 150+ years. Calculate the lifetime cost. Chain costing 1,000 hours of labor, initially plus 50 hours every 50 years for inspection and link replacement, provides 400 years of service for 1,150 total labor hours, 2.9 hours per year, averaged across its lifetime. Modern grade 80 chain costs $15.30 per meter, requires replacement every 7 to 10 years, and needs annual inspection. Over 400 years, this totals 40 to 60 replacement cycles at current costs of $600, $1,800 per replacement, $24,000, $108,000 total. Even accounting for labor hour costs, the medieval chain is dramatically cheaper across centuries, but cost structures differ. Medieval chain required massive upfront investment. Modern chain spreads cost across frequent replacements. For institutions thinking long-term, the church, nobility, guilds, the medieval model was rational. For individuals thinking short-term tenant farmers, merchants, ship captains who didn't own their vessels, the modern model seems rational because timeframes are truncated. The economic structure determines which approach seems efficient. Modern capitalism, with quarterly earnings pressures and discounted cash flow that devalues future costs, favors frequent replacement over durable goods. Medieval economic structures, with stronger intergenerational obligations and institutions designed for perpetual existence, favored one-time investments in permanent infrastructure. Neither approach is objectively superior. They optimize for different time horizons. But claiming modern chain represents technological progress is dishonest. It represents economic progress for manufacturers who profit from continuous replacement, not functional progress for users who must replace continuously. Chapter 8. The Master Who Forges Forever. In the Black Forest of Germany, a blacksmith named Klaus Zimmermann forges chain using medieval techniques. He's 67, learned the craft from his grandfather, who learned from his grandfather, creating knowledge lineage, reaching back to the 1700s, close enough to touch authentic medieval practice. His forge uses charcoal, not coal or gas. The fire reaches 1,200 degrees Celsius through hand-pumped bellows, creating blast that medieval smiths would recognize. The iron comes from a Swedish supplier producing wrought iron through traditional bloomery furnaces, one of 3 suppliers worldwide maintaining this production. Klaus forms links by hand, bending hot iron around mandrels, fire-welding the ends, testing each link by ear. A day's work produces 3 to 4 meters of finished chain. Industrial chain production outputs 50 to 100 meters per hour. The economic disparity is total, but Klaus's chain will outlast him, will outlast his grandchildren, will function when industrial chain has failed and been replaced 6 times over. He charges €200 300 per meter, roughly 10 times industrial chain costs. His clients are heritage sites restoring historical mechanisms, museums recreating period-accurate displays, and individuals who understand that €300 spent once beats €30 spent repeatedly. The market is tiny, perhaps 10 to 20 commissions annually, supplemented by other blacksmith work. Klaus has trained 2 apprentices in 40 years. One continues practicing, operating a forge in Austria. The other abandoned the craft for welding, steadier income, shorter hours, modern workspace. The knowledge transfer is fragile. When Klaus retires in 5 to 10 years, one more knowledge thread weakens. Perhaps 30 blacksmiths worldwide can forge chain using traditional fire welding techniques. Most are over 60. The craft is dying not because it's inferior, but because it's economically marginal. Society has chosen convenience over permanence, accepting continuous replacement over one-time excellence. The choice has consequences we're only beginning to recognize as our infrastructure, roads, bridges, buildings requires constant, expensive maintenance, while medieval structures stand largely unchanged. Klaus's forge is museum already, preservation of practice that mainstream metalworking has abandoned. Future generations will examine his chain the way we examine medieval chain, amazed that such work was possible, unable to replicate it, wondering what knowledge we lost when economic efficiency replaced craft mastery. Chapter 9. The Science that Proves the Past. Modern materials science extensively studies historical metalwork, attempting to reverse engineer properties and understand why medieval materials often exceeded contemporary equivalents. The findings consistently validate traditional practices while revealing sophistication that challenges replication. The Max Planck Institute for Iron Research analyzed over 100 chain samples from medieval and early modern periods, examining microstructure, composition, mechanical properties, and corrosion resistance. Their comprehensive study revealed several key factors explaining superior performance. First, phosphorus and sulfur content. Medieval wrought iron contained 0.02 to 0.05% phosphorus and 0.01 to 0.03%. Sulfur, extremely low by historical standards. Modern steel, despite refined production, often contains 0.03 to 0.06% phosphorus and 0.02 to 0.05% sulfur. These elements, even in small amounts, reduce ductility and accelerate corrosion. The medieval iron was purer, producing tougher, more corrosion-resistant material. Second, slag orientation. The fibrous slag inclusions ran parallel to the iron's working direction lengthwise in chain links. This provided maximum toughness in the direction of stress. Modern steels lack these oriented inclusions, instead having randomly distributed inclusions that provide no directional reinforcement. Third, grain structure. The repeated heating and forging refined the iron's grain structure to 10 to 50 micrometers, far finer than modern hot-rolled steel at 50 to 200 micrometers. Fine grain structure increases strength and toughness simultaneously, normally contradictory properties. Fourth, work hardening gradients. The fire welding process created hardness gradients through the link, softer in the center, harder at surfaces. This provided impact, resistance, soft core absorbs energy, plus wear resistance, hard surface resists abrasion. Attempts to replicate medieval chain using modern equipment achieved partial success. Researchers could produce wrought iron with low impurities, could fire-weld using forge techniques, could create properly proportioned links, but the combinations of skills, materials, and tacit knowledge proved difficult. The best modern replications matched 70–80% of medieval chain's performance. Impressive, but not equivalent. The remaining 20–30% performance gap traces to factors researchers cannot fully control: the precise iron composition from historical ore sources, the thermal cycles of charcoal firing versus gas forge, the hammer techniques of trained smiths versus modern practitioners, and environmental factors during forging that affected oxidation and scale formation. The medieval chain represents optimized technology, centuries of empirical refinement, producing near-ideal results within the constraints of available materials and energy. Modern technology can explain why it worked, but struggles to replicate it because the optimization occurred through evolutionary selection across generations, not through theoretical analysis and rapid prototyping. Chapter 10. The failure modern metallurgy hides. Industrial chain manufacturing produces consistent, affordable product through processes optimized for volume and cost. But the optimization creates vulnerabilities that manufacturers don't advertise. Modern chain is electric flashbutt welded. The link ends are heated by electrical resistance, then pressed together under mechanical force. The weld occurs in milliseconds, creating consistent joints suitable for automated production. But the weld zone has different microstructure than the parent metal. The rapid heating and cooling creates large grain structure, brittleness, and internal stress. These welds are stronger than required by specifications initially, but they're vulnerable to fatigue, corrosion, and stress concentration in ways fire welds aren't. Industry testing focuses on initial strength, not longevity. A chain that tests at 120% of rated capacity when new is approved, even if degradation will reduce strength to 70% within 5 years. The testing protocols don't examine long-term performance because economic models assume replacement before degradation becomes critical. The galvanization zinc coating applied for corrosion protection has similar issues. The coating is applied by dipping finished chain in molten zinc. This creates protective layer that works excellently until it fails. Zinc coating thickness is typically 50 to 100 micrometers. In marine or industrial environments, this coating lasts 3 to 7 years before showing significant wear. Once breached, the underlying steel corrodes rapidly because the galvanic relationship between zinc and steel accelerates corrosion at damaged points. Medieval wrought iron needed no coating. The material itself resisted corrosion through low impurity content and passive oxide layers that formed protectively. When corrosion occurred, it proceeded slowly and uniformly, not accelerating at specific points. Reports of chain failures rarely make news unless catastrophic accidents result. But data from industries using chain extensively, shipping, construction, entertainment rigging show concerning patterns. Rigging inspectors report finding chains that test below specification after 4 to 6 years, despite meeting all maintenance requirements. Construction safety databases document increasing incidents of chain failure under rated loads. The maritime industry has noted rising anchor chain replacement frequency. None of this suggests modern chain is dangerously defective. Safety factors and inspection intervals prevent most failures. But it reveals that marketed chain lifespans are optimistic, that real-world performance falls short of specifications, and that the replacement cycle is accelerating. We're building infrastructure and systems dependent on components with shorter effective lifespans than designed, creating maintenance burden that compounds as facilities age. Chapter 11. The regulation that mandates replacement. Modern industrial safety regulations require periodic chain inspection and retirement based on age, use cycles, and measured degradation. These regulations serve legitimate safety purposes, preventing failures that could kill people. But they also encode assumptions about material durability that favor continuous replacement. OSHA standards for chain slings require retirement when Stretch exceeds 5% of original length. Wear reduces diameter by 10%. Links are bent or twisted. Welds show cracks. Or the chain exceeds 5 years of service, regardless of condition. That final criterion, age-based retirement, assumes the material degrades predictably with time. This is true for modern chain, but wasn't true for medieval chain. The regulations don't distinguish because medieval chain isn't commercially available. Standards, written for available materials, become universal requirements. Similar patterns exist across industries. Maritime chain standards, construction safety codes, amusement ride regulations all specify inspection intervals and retirement criteria based on modern material properties. The assumptions embedded in these regulations make traditional chain non-compliant even when its performance exceeds modern equivalents. This creates regulatory lock-in. Even if someone wanted to manufacture traditional wrought iron chain, it couldn't be used in most commercial applications because it wouldn't meet specifications written for modern materials. The superior material is prohibited by standards assuming inferiority of anything non-contemporary. Reform would require performance-based standards, specify the required strength, corrosion, resistance, and fatigue life, then allow any material meeting those requirements. This would permit traditional materials while maintaining safety. But changing established standards is difficult. It requires committee consensus, industry input, and regulatory agency approval. Industries satisfied with current standards resist changes that might require new testing or qualification procedures. The result is regulatory ossification standards that reflect 1,960 seconds, 1,980 seconds. Materials technology persist, unchanged, while both better and worse alternatives are developed. The regulations serve safety and serve industry replacement cycles, simultaneously protecting users and ensuring continuous chain purchases. Chapter 12. The Cathedral Bell That Still Rings. In Cologne Cathedral, 5 bronze bells, the largest, weighing 24,000 kilograms, hang from wrought iron chains installed when the cathedral was completed in 1880. These chains, forged using traditional techniques already archaic when installed, support bells that swing daily, creating dynamic loads far exceeding static weight. After 144 years, the chains show minimal wear. The cathedral maintenance records document annual inspections. The chains are cleaned, examined for cracks or deformation, and tested using ultrasonic methods. Every test confirms structural integrity, unchanged from installation. The same cathedral installed modern steel cable in 1,950 seconds to support scaffolding during restoration. Those cables required replacement in 1975 and again in 2003. The modern materials lasted 20 to 30 years. The traditional chains have lasted 144 years and counting. Similar patterns appear at cathedrals across Europe. Notre Dame in Paris, before the 2019 fire, had bell chains from 1,850 seconds still in service. Westminster Abbey has chains from 1700s. Salisbury Cathedral has chains from 1200s, now retired not from failure but from museum preservation. These aren't exceptional cases. They're typical results for properly forged wrought iron chain in cathedral bell applications. The dynamic loading is severe. A swinging bell creates forces 2 to 3 times its static weight, cycling thousands of times daily, millions of times over decades. The chain must absorb this without fatigue, without wear, without failure. Medieval chain handles this indefinitely. Modern chain, subjected to identical loading, shows fatigue cracking within 30 to 50 years. The explanation is material science. Wrought iron has no theoretical fatigue limit. It can withstand cyclic loading indefinitely below certain stress threshold. Modern steel has finite fatigue. Life eventually fails regardless of stress level. The difference comes from microstructure. Wrought iron's fibrous slag inclusions blunt crack tips, preventing fatigue crack propagation. Steel's homogeneous structure allows cracks to propagate unchecked. Cathedral maintenance engineers recognize this. When replacement becomes necessary from accidental damage or preservation concerns, They source traditional wrought iron chain from specialized suppliers if possible. When unavailable, they oversize modern chain, accepting that it will require more frequent replacement. The additional cost of frequent replacement is accepted because regulatory and insurance concerns prevent using old chain indefinitely, even when testing confirms it remains safe. Chapter 13. The knowledge that dies in silence. The craft knowledge for traditional chain making exists in perhaps 30 to 50 people worldwide. Most are over 60. Few are actively training apprentices. When they die, the knowledge dies not completely, but substantially. Written documentation exists, historical texts describing processes, modern analyses explaining metallurgy, videos showing techniques, but crucial elements resist documentation. The judgment of proper welding heat too cool and the weld fails, too hot and the iron burns. Texts say yellow-white heat, videos show the color, but neither conveys the exact recognition of the moment when heat is perfect. That recognition develops through hundreds of repetitions, feeling the heat radiating from the forge, seeing subtle color shifts, learning the few-second window when conditions are ideal. The hammer rhythm for fire welding: rapid blows with decreasing force, starting heavy to establish upset and gradually lightening to finish the weld. Texts specify 3 to 4 blows per second tapering force, but the actual rhythm is musical, felt rather than counted, varying with iron temperature and link size. An experienced smith hears when the rhythm is wrong, even when watching another smith work. The sound of proper iron quality, the ring revealing internal structure. Descriptions exist, audio recordings exist, but learning to distinguish subtle variations requires years of listening to thousands of test strikes, calibrating ear and brain to recognize quality acoustically. These tacit skills develop only through extensive practice under guidance of someone who already possesses them. Reading about skills isn't sufficient. Watching videos isn't sufficient. You must practice, receive feedback, gradually internalize the judgments until they become intuitive. This requires apprenticeship, months or years, working alongside masters, repeating processes, making mistakes, being corrected, slowly developing competence. Modern economic structures don't support this. Apprenticeships are unpaid or low-paid, lasting years. Young people have educational debt, living expenses, opportunity costs. Spending 2 to 4 years learning chain forging for uncertain career prospects is economically irrational when welding certification takes 6 months and provides immediate employment. The few who pursue traditional blacksmithing do so despite economic logic, driven by passion or philosophical commitment to preserving knowledge. This ensures the knowledge survives in minimal form, enough practitioners to maintain continuity, but not enough to serve any significant market or ensure robust transfer to next generation. We're watching knowledge extinction in slow motion, not sudden collapse, but gradual erosion, as each generation contains fewer practitioners, less comprehensive skills, more reliance on documentation rather than embodied expertise. Chapter 14. The metal that comes from earth. The iron medieval smiths used came from bog ore, or surface deposits, relatively pure iron oxide, that could be smelted in bloomery furnaces using charcoal. These sources produced iron with characteristics modern blast furnaces cannot replicate. Bog iron forms when iron-rich groundwater reaches surface, oxidizing and precipitating as iron hydroxide in wetlands and streambeds. This iron is nearly pure, free from the sulfur, phosphorus, and other impurities present in deep geological deposits. Harvesting bog iron required no mining, just collecting surface nodules. The bloomery furnace stone or clay structure, filled with alternating layers of charcoal and bog iron ore, produced bloom. Spongy mass of nearly pure iron mixed with slag. The smith hammered this bloom while hot, expelling slag and consolidating iron into workable bars. The process was labor-intensive and inefficient. Perhaps 60% of iron was lost to slag. But the resulting wrought iron was exceptionally pure, containing properties modern steel lacks. Modern blast furnaces use deep-mined ore containing significant impurities. Refining removes most impurities, but not all. Trace elements remain, affecting properties. The modern process is far more efficient, 90% plus iron recovery, but produces material with different characteristics. Some Swedish and German suppliers maintain bloomery furnaces specifically for producing traditional wrought iron. They mine bog iron from historical collection sites, run charcoal-fired bloomeries, and produce material nearly identical to medieval iron. The production is tiny, perhaps 10 to 20 tons annually worldwide, versus 2 billion tons of steel. The cost is extreme, $20.40 per kilogram versus $0.50 per kilogram for steel. Only specialist applications, historical restoration, premium blacksmithing, cultural preservation justify the cost, but the material's properties validate the expense. Traditional wrought iron outperforms modern steel for applications requiring toughness, corrosion resistance, and longevity. It's not stronger, mild steel exceeds wrought iron's tensile strength, but it's tougher and more durable. The performance differences matter for long service applications. Architectural elements expected to last centuries. Marine hardware exposed to harsh conditions. Mechanical components subject to vibration and fatigue. For these applications, paying 40x more for material that lasts 10x longer is economically rational. But markets don't optimize for century-scale durability. They optimize for initial cost and near-term performance. So the superior material remains niche, serving minuscule market while inferior alternatives dominate. Chapter 15. The chain that refuses to break. You cannot buy traditional wrought iron chain commercially. The handful of smiths producing it serve heritage sites, museums, and rare private clients willing to pay premium prices. For practical purposes, the material doesn't exist in modern supply chains. This isn't technological regression. We could produce it if we chose. We have the knowledge, the equipment, and the capability. We don't produce it because economic structures don't reward 400-year durability. They reward products that require replacement every 7 to 10 years, generating continuous revenue streams. The lesson the chain teaches transcends its specific engineering. It's a lesson about time horizons, about design philosophy, about what we optimize for when we build things. Medieval chain was optimized for permanence. The blacksmith expected his work to outlast him, to serve his children's children. The chain wasn't product, it was legacy. Modern chain is optimized for economic efficiency. The manufacturer expects replacement cycles, generating recurring revenue. The chain isn't legacy, it's consumable. Neither approach is objectively wrong. They serve different purposes. But claiming modern chain represents progress is dishonest. It represents changed priorities, not improved technology. The medieval chain, hand-forged, fire-welded, acoustically tested, geometrically optimized, embodies knowledge accumulated across centuries of refinement. Each link contains the experience of thousands of smiths, each failure analyzed, each success replicated, each technique gradually perfected. That knowledge is slipping away. The smiths who carry it are aging. The economic structures that could support its transmission don't exist. The cultural values that prize permanence over convenience have eroded. We're losing the ability to make things that last, not because we've forgotten the techniques they're documented, but because we've forgotten why permanence matters. The chain waits in castle drawbridges, cathedral bell towers, museum collections. It waits as silent testimony to what's possible when craftsmanship prioritizes longevity over efficiency, when users think in centuries rather than quarters, when material quality matters more than manufacturing cost. It won't wait forever. The last traditional smiths will die. The knowledge will become archaeological curiosity rather than living practice. The chain itself will outlast us, those medieval links still functioning after 800 years, but our ability to create their equals will vanish. Unless we remember that the most valuable technologies aren't always the newest, that sometimes the old ways worked better, and that the chain that never breaks is precisely the chain we've stopped making because it breaks our economic models by never breaking itself.